Hello, welcome again to this online course on fundamentals of composites and cellular materials. So, for last few classes we are discussing on the topic of mechanics of composite materials, and in this series today is our last class where we will discuss about unidirectional discontinuous fibers. Okay. So far we have discussed about continuous fibers, and then in continuous fibers if we apply longitudinal loading or transverse loading, what are the different parameters, for example, what are the elastic moduli values or tensile strength of composite material, resulting tensile strength of composite material, those parameters we have discussed how to calculate, and then we have discussed about certain examples where it has been shown that if we have given certain parameters, then how ultimately we can calculate the different mechanical properties of composite material based on that. Those aspects we have discussed in last few classes, and then we moved to from continuous fiber we moved to discontinuous fiber, and then initially when we are talking about discontinuous fiber, that means short fiber, there we discussed about unidirectional discontinuous fiber. Okay. That means that fibers are short fibers, that means these are not continuous, but then those are unidirectional in the sense either they are, in fact they are mostly aligned to the direction of longitudinal loading. So, we will continue with that, but in this class today we will discuss about random distribution now. Okay. It is not the discontinuous fibers, the short fibers are not unidirectional anymore. If we have random distribution of short fibers, then how do we calculate the different parameters, that is the modulus and other parameters, that we will be discussing, and then we will concentrate on certain problem solving. So, let us start our class today. So, when we are talking about so let us talk about now we have a composite material, and here the fibers are short, however, they are aligned in a particular direction. Okay. So, we will start with this condition, and then we will move to a condition where in a composite material these short fibers are not aligned, they are randomly distributed, something like this. Okay. So, let us start with the first case. Now, if we want to calculate, so now in this direction if we apply load and if we try to measure the modulus, we call it as E11. Similarly, if we are applying load in the transverse direction like this, in that case we get the value of E22, right. So, now based on a particular equation, set of equations basically given by Halpin and Tsai, what we get is that E star is equals to E m, where E m is the modulus of the matrix, E m multiplied by 1 plus 2 xi eta V f. I will explain all these terms. 1 plus 2 eta 2 xi eta V f over 1 minus eta V f. Now, what is xi here? Xi is basically the aspect ratio in the aspect ratio of reinforcement in the loading direction, that is very important, in the loading direction. All right. and in this E star basically this is basically from here you can calculate E11 or E22. Okay. Now, this xi value and eta value will change with the change in loading direction. For example, if we are applying longitudinal loading, then this xi longitudinal would be equals to, now you can understand. So, in this case the aspect ratio, so it is now it is this particular direction is longitudinal loading. So, in this case you can concentrate on one fiber, and this fiber, the aspect ratio of this fiber will be basically L of f over df, where L is the length of fiber, Lf is the length of fiber and df is the diameter of fiber. Okay. And the value of eta L is equals to Ef over Em minus 1 over Ef over Em plus 2 xi. Okay. So, that is the value of eta. Okay. We can just say this is the eta value. Now, the moment we try to calculate eta L, because of the change in xi value, it will be as Ef over Em minus 1 by Ef over Em plus 2, now it is Lf over df. So, accordingly we can get the value of, so now if we try to calculate using all these equations, if you try to calculate E11, okay, so you can see then it will be equals to Em over 1 plus 2. Now, it is we are talking about E11. So, this xi will be xi L. So, xi L, the value of xi L from here you can get is Lf over df multiplied by eta L, and this and then multiplied by Vf over 1 minus eta L Vf. Okay. And this eta L value we can get from this equation here. So, now we can calculate the value of modulus in the longitudinal direction. Similarly, we can also calculate the value of the modulus value of the composite material in the transverse direction, which is E22, and E22 would be equals to Em multiplied by, so we will be using again the similar equation. However, in this case the value of xi t, that is xi transverse, is equals to how much it will be? It will no longer be Lf by df, it is still the aspect ratio, but now you can consider, you can think about, let us consider a single fiber, and if you are applying, let us say, loading in the direction of transverse, let us consider this is transverse, then the fiber is not aligned like this. So, it is not the alignment, but now you will be seeing the cross section of the fiber. Okay. So, the fiber is basically aligned like this, that means you will be seeing the cross section of the fiber when the loading is being applied in transverse direction. I hope you get it. So, in this case, what is the aspect ratio? So, now it will be considering, if you remember in the last class I mentioned, in transverse direction the fiber is basically being considered as a spherical hard particle. Okay. So, in this case the aspect ratio is basically d of fiber over d of fiber, which is basically equals to 1. Okay. So, from here you can see that how the xi value is changing depending upon the direction of loading, either it is longitudinal or transverse. Based on those loading directions, the xi L value and xi T value are changing. Similarly, so now if you consider about eta T value, that is eta value in the transverse direction, so it will be following the same equation. It will be E f over E m minus 1, there is no change here. However, in the denominator it will be E f over E m plus 2, because now L f d f is equals to 1. So, basically it is 2. So, now you can use all these values in this equation and you get E m is equals to 1 plus 2, because the xi value is 1 now, multiplied by eta t into V f over 1 minus eta L V f. Okay. So, that is how you get the value of E 11 and E 22. Now, why is this important? Why you are talking about calculating E 11 and E 22? Because ultimately we want to calculate the modulus of this combination, where the fibers are distributed in random fashion. There is no alignment of fiber here, all the fibers, as you can see here, in a random distribution. So, in this case, either way you apply load, if the load is being applied in this direction like this or like this, there is no longitudinal direction or transverse direction. So, the modulus would be conjugation of E 11 and E 22 value in this case, because each fiber, so you can consider this particular fiber, this fiber will be contributing to E 11 as well as E 22 because of its alignment in a particular fashion. It is not aligned towards the longitudinal direction, it is not aligned towards the transverse direction as well. So, when you try to calculate the value of, you can write it as E random. Now, we are talking about E random, and there you have to consider both the value of E 11 and E 22. So, the value of E random will be a conjugation of E 11 and E 22, and that will be equals to 3 by 8 multiplied by E 11 plus 5 by 8 multiplied by E 22. Okay. Similarly, you can get the value of G random, which is basically the shear modulus. So, this is elastic modulus and then we are talking about shear modulus G random, and that will be equals to 1 over 8 E 11 plus 1 over 4 multiplied by E 22. And from here, from the value of E and G random, you can get the value of Poisson's ratio in. Now, it is, you can see here the Poisson's ratio is also, there is no direction here. Okay. You do not know which is longitudinal and which is transverse. So, again the Poisson's ratio will be also random. So, nu random would be now equals to E random over G random, E random over G random, and a 2 factor will come here. So, E random over 2 G R minus 1, that is the value of nu when you are applying direction, when you are applying a loading and the distribution of fiber is random. So, basically using all these equations, ultimately your aim is to find out the value of the different parameters when there is random distribution, and ultimately using these 3 equations you can get the values. But to come into this, to get these values, you have to also calculate all these values initially. We will solve a problem on this using this theory, this model, and then I hope it will be much more clear to you. So, let us move on. So, now let us go into certain problems and we will see how to solve those problems. Okay. So, I have provided all these equations in the slides. So, you can have a look on these equations. Okay. And then I have talked about this particular 3 equations which actually you can apply to find out the value of elastic modulus, shear modulus and Poisson's ratio when the distribution of fiber is such, it is random. Okay. And you can see again, while getting to these equations, there are certain assumptions, as you can see, that we are considering the fiber cross section as circular. Okay. That is why we are talking about LF and DF. Okay. So, the fiber cross section is circular, fibers obviously are uniformly distributed throughout the matrix. It is random, but there is no cluster formation. That is what we are trying to say here when we are saying uniform distribution. Uniform distribution means they may not be aligned in a particular direction, but there is no cluster formation as well, or there is there is no concentration of fibers in a certain locations, so that there will be no cluster formation and those things. So, that is what we are calling it as uniform distribution. Interfacial bonding is perfect. So, we are not considering any kind of interfacial delamination while coming to these equations. And another very important factor is that the voids, there is no voids or porosity in the matrix. So, the matrix is basically porosity free or void free. Okay. So, now let us discuss few problems on the theories which you have learned so far. In the last class, if you remember, we talked about this particular case where where this so we have this composite material where the fibers are short fibers, that means discontinuous fibers, but these are aligned in the longitudinal direction. So, we have found out the different theories. So, how do we ultimately how do we calculate sigma LTU, that means sigma tensile stress in the longitudinal direction, okay, and tensile ultimate of the composite material. That we discussed in the last class. So, based on those theories, we will try to solve this problem. What it says is that a unidirectional fiber composite contains 60 volume percent of carbon fiber. So, the fiber here is carbon fiber and the volume percent already is given 60 volume percent. That means, Vf is equals to, it has been given as Vf as 0.6, right. And then the matrix has been told using the fiber properties below. So, fiber properties have been mentioned here, fiber diameter has been mentioned, then the tensile strength of the fiber has been mentioned and the modulus of the fiber has been mentioned. So, based on these properties and matrix properties also have been given here, determine the longitudinal tensile strength of the composite for the following cases. Okay. Longitudinal tensile strength means what? Basically sigma LTU, you have to calculate sigma LTU. Now, there are two conditions have been given. In one case, the fibers are all continuous. In the second case, however, the fibers are not continuous, but short fibers with certain length and then tau I values are different. So, let us first address the first issue, that is if the fibers are all continuous. Okay. Now, what we need to actually check here is that the first point we have to see is that, though it is quite clear from here, but still we need to check that the value of epsilon m u, is it more than or less than epsilon Fu. Just to check, though we all know in most cases this epsilon mu is higher than epsilon Fu, but still let us check it once before we proceed further. So, what is the value of epsilon mu? If we try to calculate epsilon mu is equals to, what is that? You get, so epsilon mu is equals to sigma mu over E of the m, right. So, you can calculate epsilon mu. So, sigma mu already has been given here, you can see sigma mu or sigma my is basically same thing. So, that is 138 MPa over Em has been given here, which is 3.45 GPa, and then ultimately from here you can calculate using the but you have to take care of the units. So, the value of epsilon mu would be coming as 0.04. You can calculate it and check, it will be coming as 0.04. Similarly, you also calculate the value of epsilon Fu, and that will be equals to similarly sigma Fu over E of F, and from here you can get those values. So, sigma Fu is given as 2480 MPa over Ef is given as 345 GPa. So, from here you can find out ultimately it will be around equals to 0.0072. So, you can see from here that epsilon mu is obviously more than epsilon Fu. That means fiber failure will take place first. So, that is very important, fiber failure takes place first. So, that is important. Why? Because now if you remember the equation of sigma LTU, so let us look into this equation. Now, sigma C of composite material is what? In case of continuous, we are talking about the first case where the fibers are continuous fiber. Okay. So, when it is continuous fiber, so in that case sigma C is equals to what? Sigma C equals to EF, sorry not EF, we are calculating sigma C. So, it will be basically sigma F, right, not E, but it will be sigma F multiplied by Vf plus sigma m multiplied by 1 minus Vf. That is a universal equation, as you understand. Okay. Now, when you try to from here, when you try to get sigma LTU, okay, that means when the fiber is failing, the composite material is failing, in that case this sigma F is basically sigma F ultimate multiplied by Vf plus sigma m ultimate multiplied by 1 minus Vf. Am I correct here, or there is some mistake in this equation? So, you see here it will not be sigma mu. Why? Because if you remember, I have discussed it vividly that when the fiber fails, as you can see from here, the fiber fails early than the matrix. That means, when the fiber fails, the matrix will not be experiencing the ultimate tensile strength of the matrix, rather than it will be what? It will be sigma m dashed, right. Okay. Sigma m dashed means at the failure strain of the fiber, how much stress is being experienced by the matrix. Okay. So you have to find out the value of sigma m dash now. Now, how do you get the value of sigma m dash? Sigma m dash is equals to again E of m, yes, string modulus of matrix multiplied by strain of matrix, but at what strain? At what the fiber fails, that is epsilon f, okay, or you can say epsilon fu. Okay. So, that will be equals to, you can again plug in the values, epsilon em equals to 3.45 GPa multiplied by epsilon fu, you have already calculated epsilon fu, that is 0.0072, and from here you get the value of sigma m dust as 25, 25 MPa, approximately 25 MPa. So, now you have the value of sigma m dust. Now, you have all the values, you have sigma fu, you can see sigma fu has been given here 2480 MPa multiplied by the volume fraction of the fiber, which is basically 0.6 plus sigma m dust you have calculated here. So, this is 25 MPa multiplied by 1 minus Vf, which is 0.4. So, ultimately from here you can get the value of sigma LTU, and that will be equals to around 931 MPa. So, that is the first answer you have got as 931 MPa. Okay. So, now the next thing is, you can see, to address the second problem. Okay. I hope the first one you have got everyone correct. Okay. You please go through it once more, so that you understand it quite well, okay, because such kind of problems you have to solve when you appear for exams, or in your real applications also. Such problems have to be solved. Okay. So, now let us go into the second one. Okay. So, let me just erase these things from here, and okay, and then what we do actually, we go to the second problem. And the second problem, it says the fibers are 3.17 millimeter long. So, now it has been said here is that F, so LF is equals to 3.17 mm. Now, before trying to find out the value of sigma LTU, what we need to do is that we need to calculate the value of LC, that is critical length, because you have to see that the LF is more than the critical length of fiber or less than. Based on that, the equation for sigma LTU will change, right. So, LC you have to find out. Now, how do you find out the LC value? You know the equation for LC, that is sigma Fu over 2 tau I multiplied by LF, sorry, it will be dF, it will be dF, yes, diameter of the fiber, right. So, you can plug in the values now. Sigma Fe, sigma Fe has been given here 2480 MPa, and you can see here there are 2 taus value given. Okay. So, for each cases you have to find out the value of LC. So, let us look at the first one, which is 4.11 MPa 2 multiplied by, and then the diameter of fiber has been given as 8 micrometer. Okay. So, 8 into 10 to the power minus 3 millimeter, and from here you can calculate the value of LC. What you will be seeing is that LC will be coming around 2.414 MPa, sorry, millimeter. That means, you can see that LC is, what is here, LF is more than LC, that you see. So, now you have to find out the value of sigma LTU. Now, sigma LTU is equals to, as you know, sigma FU VF plus sigma M dash into 1 minus VF. Now, it is not sigma FU actually, because now it is not continuous fiber, it is short fiber. So, to find out the value of average sigma FU. Okay. And what is the value of average FU? That is average FU, sigma FU, this sigma FU average depends on the value of LC, LF basically. Is it more than LC or LF less than LC? Okay. In our case, LF is more than LC. So, we use this equation sigma FU average is equals to basically sigma FU multiplied by 1 minus LC over 2 LF. And that is what we have done in the last class. We have found out this equation in the last class, that sigma FU average is equals to sigma FU multiplied by 1 minus LC over 2 LF when LF is more than LC. If LF is less than LC, in that case what will be happening? Sigma FU, if you remember, sigma FU average is equals to what? It will be equals to basically. So, you can find out from this equation only, sigma FU average would be equals to this 2 term will go out. So, it will be basically tau I multiplied by LC over dF. So, that is actually the value of sigma FU average when LF is less than LC, but when LF is more than LC, then you use this equation. So, now you can plug in these values here, sigma FU multiplied by 1 minus LC over 2 LF multiplied by VF plus sigma M dash multiplied by 1 minus VF. Now, you know the value of sigma FU, LC also you have calculated, LF is given, VF is 0.6, sigma M dash you have calculated earlier, and then VF, so you know all the values here, okay, of the parameters. So, from here you can get the value of sigma LTU. Similarly, again you can calculate the value of LC when the interfacial strength tau I is changing, and you need to check that the value of LF is more than LC or less than LC in this case, and based on that you use this equation or this equation depending upon the value of LF, and then from there you get the value of ultimately sigma LTU. So, that is how you solve this problem. Okay. All right. Let us move into one more problem, but in this case we will talk about random distribution. So far we were discussing this problem talks about fibers are aligned. Okay. Here short fibers, but it has not been mentioned here, but basically we have considered here that the fibers are aligned. Let us go into a problem which is basically talks about random distribution. So, let us move on and I will quickly explain this problem. So, you can see here, okay, what has been done, what is the problem says is that consider a sheet molding compound composite, some name has been designated, containing E glass fiber in a thermoset polyester matrix. So, you can see here that the fiber is E glass and the matrix is polyester, and then this data has been provided, and ultimately what it says, calculate the tensile modulus, shear modulus and Poisson ratio for the material. Now, you see here LF has been given, that means this is short fiber, okay. DF has been given, okay, and the density of the materials have been given. Why the density values have been given? Because if you see, it is not volume fraction, but here it is mass fraction or weight fraction rather to say, this is weight fraction. So, what you have to do now, from the weight fraction you have to get the value of mass fraction. Okay. Sorry, from the weight fraction you have to get the value of volume fraction, I am sorry. Okay. And then if you remember in the last few minutes back I was discussing about all these equations. Let me go back to those equations. So, you can see you have to apply all these equations and ultimately these equations to find out the value of, as it say here, that the value of this it says the tensile modulus. So, basically this tensile modulus is nothing but E random. Similarly, shear modulus means G random and Poisson ratio is nu random. So, as I was mentioning earlier is that first you calculate the value of this V f from the weight fraction value. Weight fraction has been given. So, you calculate the value of V f. So, you can see here weight fraction over the density, weight fraction over the density of the fiber, and then weight fraction, that is the matrix over the density of the matrix, and then ultimately you get the value of the volume fraction. Okay. And then ultimately you have to calculate the value of E 11. In order to get the value of E 11, eta L has been calculated, okay. E f over E m calculated. So, because all these equations have to be plugged in. Okay. So, that is how it has been done. Okay. And then similarly eta t has been calculated, that is transverse longitudinal, and then E 22 has been obtained by using the Hall-Pincer equations. And then finally, using E 11 value and E 22 value what you got earlier, you get the value of E g and nu when the fiber distribution is random. Okay. So, that is how actually you solve these problems. Okay. So, let us move on now. So, with this actually I would like to conclude today's class. So, in today's class what we have discussed first? We have discussed first the different equations to calculate the values of mechanical properties, certain mechanical properties when we have discontinuous or random distribution of fibers, and then we solved two different problems. In one case it is, in both cases the fibers are short fibers. However, in one case it is discontinuous, other case it is continuous. So, in both cases how can we find out the values of the modulus values of the and ultimately the strength value also of the composite materials. That is what we discussed in today's class. So, with that basically we end the session on mechanics of composite materials. So, now there will be mechanics of cellular materials will be coming after these classes, and then we will talk about advanced composites. Okay. So, I end the class today. Thank you all.